Now, today we are going to the next type of optimization technique, that is the solving the unconstrained optimization problem using numerical optimization technique. The basic advantage of numerical optimization technique is that we need not to have the function is continuous within the domain of interest. Now, as we have seen in the classical optimization technique, we were finding out the first order derivative and the second order derivative. We had to depend on those values. That is why there was a necessity to have the function is continuous, but here we do not have that necessity. Function can be discontinuous, it can be piecewise continuous, it can be discrete. For the discrete optimization problem also very nicely we can find out the optimal solution. Now, today we will tell you our series of techniques for solving numerically the nonlinear programming problem with single objective function with single variable and there is no constraint. Now, for solving this, for applying the numerical optimization technique, we need to have one assumption that is necessary, that is must, that function must be unimodal within the given domain. Now, we should have the prior knowledge about the pattern of the function, then only we can apply it. If we do not have the prior knowledge of the functional values, then we have to check the convexity or concavity of the function within the range, and there we have to guess that how function is behaving, and then only we can say the function is unimodal within a certain range, then only we can apply the numerical optimization technique. That is the in detail, I will talk on that later on. But one thing is that we need to have the interval of uncertainty and function must be unimodal. Now, what is interval of uncertainty? Interval of uncertainty is referring to that interval where the optimum may lie. Either maximum or minimum we are trying to find out. That is why if we have the information that maxima or minima can lie within this range in the given x, we are considering the function of single variable. That is why within the real line, if we are having the lower limit and upper limit of the interval where the optimum may lie, then that is being named as the interval of uncertainty. That is why two things should be known beforehand. One is that interval of uncertainty, and second is that we need to know the function is unimodal within that interval of uncertainty. Another thing is necessary for few cases like Fibonacci method and few other methods, we need to know that how many iterations we need to do. Actually, the numerical optimization technique is the thing we are using the iterative process. We are starting from a guess point, we are checking whether the point is optimal or not. If the function is not optimal, we are going to the next point, that is the approximation again for optimal. If it is not even optimal, if there is a provision to improve the value of the objective function, then we approximate the third one. In that way, we apply the iterative process. This is a process of iteration. And once we will find out a sequence of values of the approximate value of the optimal solution, then we will see that function is the values are converging to a point, and that point will be declared as the optimal solution of the given function. But the whole numerical optimization technique is very much dependent on the region elimination process. Region elimination process, I have given certain idea in my last class on interval hubbing method. There you got certain idea what is the region elimination technique, but just today I will formally introduce that technique to you, how mathematically we are establishing the region elimination process. What is that? We are starting from a guess point and we will find out the sequence of improved solution after eliminating the region. That means, we are reducing the interval of uncertainty and we are reducing further and further. We are trying to reach to a smaller interval of uncertainty, and at the end we will get the interval so small that that interval can be declared, or the middle value of that interval can be declared as the optimal solution. Okay? That is why we are applying that method. Now, let us consider this function. This function is this one, it is clear that within a and b the function is unimodal. That is why my interval of uncertainty is a to b, that is the lower limit is a, upper limit is b, and we are having the point x naught, and this is my initial guess point, and the next guess point, through the method we will find out the next guess point, and the next guess point is x double prime, this is, it is this one. Okay. Now, what we could see that functional value is increasing from x double prime to b. That is why if we are searching for the minimum of the function, we know the function has a mode within the range, and we are trying to find out the minimum of the function. That is why we are sure that within x double prime to b, the function cannot have the minimum value. That is why we will eliminate that region. That is why the process is being named as the region elimination technique. We will eliminate in the next iteration, we will have the lesser sized interval of uncertainty. That is why the next interval of uncertainty would be a to x double prime, alright. This was initial and this would be the next. Now, if this is the next level of uncertainty, then let us move to the next function. Next case, what we could see here that from now I am changing the values, I have renamed the values, x double prime I have given as b, x prime is my initial approximation again, that is x double prime from the previous iteration. Now, here the x double prime is my new finding in this iteration, alright. That is why again we are finding out the functional value. What we could see that from a to x prime function is increasing, and we are not able to see the difference, we really do not know what will happen from x double prime to b. That is why better not to discard that interval, let us discard the interval a to x prime, because we are sure minimum cannot lie there. That is why we are discarding this, and my next interval of uncertainty would be this one. Alright, clear? Now, again we are renaming x prime as a, b is as it is, x double prime as x prime, and we are moving to this. That was my initial. Now, in the next, what we could see here that x prime now my a is here, the previous one, alright. What we could see that we are having the same value at x prime and x double prime. That is why we are sure that there must be certain ups and downs within x prime and x double prime. Beyond x double prime function is increasing, because we could see the value. That is why we will declare that the minimum is lying within the x prime and x double prime. That is why my region elimination would be, I have eliminated the region and my next interval of uncertainty would be x prime to x double prime. Now, the whole process can be just mathematized in this way. Just you see, we are considering 2 points x prime and x double prime, and these are within the range of interval of uncertainty a to b. Now, if x double prime is greater than f x double prime, we are discarding the interval a to x prime, and we are taking the new interval of uncertainty, rather we are guessing the optimum may lie within x prime to b. That was the first figure. The second figure, if f x prime is lesser than f x double prime, we are declaring the new interval of uncertainty as a to x double prime. And in the third case, if x prime is equal to f x double prime, then we are eliminating both the sides of the interval, that is from a to x prime and x double prime to b, and we are declaring a new interval of uncertainty as x prime to x double prime. That way we will proceed further and further in the similar way. Now, few things are there. One thing is that how to select the first initial guess point, that you need to know, and the second is that how to reach to the next point. Once we are having the initial guess point, how to reach to the next point, that is the unknown thing for us. Now, how to solve this kind of problem? That is why we are learning a series of methodologies, and as I was mentioning this part in the last class, that this is the series of methodologies available, and in the numerical method I will explain to you the unconstrained search, Fibonacci, golden section, etc. And there is another series of methods are there on interpolation. I will mention one of that in my classes. Now, I am coming to the interval halving process. I need not to explain this method to you. Just let us see how we are eliminating the region for this. Okay? We are applying this methodology. We are taking the same function we were considering before in the last class, and that was the function was 125, 0, 0, that function, that is the orange plant problem. Now, there was a functional values were given to us, we are using those function only, and from the function itself we are getting that from 0 to 20 function is unimodal. That is why we are breaking into 4 parts, 0 to 5, 5 to 10 and 10 to 15 like that. Okay? And we could see the functional values at 0 was 12500, at 20 it was 13500. You can get the values just after substituting the value of x. This is x 3500, 14000 and 14000. What we could guess here? We could see that from here, if this is my x naught, this is my x 1 and this is my x 2, you could see that f 2 is same as f naught, rather I can say less than equal to than f naught, alright, in general. What else we could see? f 1 is less than f naught. Then which process shall we consider? We will consider the third one, because this is a maximization problem. Whatever inequality relation we took for the minimization, for the region elimination, for maximization problem, that is the reverse one. That is why we are sure the optimum cannot lie from 0 to 5 or 15 to 20. That is why we will eliminate this region. My new interval of uncertainty would be from 5 to 15. Okay. Again we will just divide it into 4 parts, 7.5, 12.5. Let us write down the functional values here. For 5 we know this is 13500, for 7.5 it is 138, 12.5, for here 14000, for this point 14062.5, and here in the 15 it is 14000. We are finding out the maximum value. Alright. What we could see here, that functional value is increasing here, after that it is increasing further, then it is decreasing. That is why from here we can say that f1, this value is lesser than f naught and lesser than f2. Alright. That is why my new region of uncertainty would be from here to here, 10 to 15, I will discard it. Okay, I will proceed further. In this way I will proceed further. 10 to 15 I will go, I will consider 12.5, I will consider 11.25, and here it is 13.75, and we will find out the functional value. And we will see, if we just proceed in this way, we will get a small interval in the region where 12 is lying, because through the classical optimization technique we found the maximum value is lying at 12. Alright, 12 or 13, because 12.5, that is why it could be 12 or 13, we are not sure which one gives us the better solution. And we will just through this process, if we proceed, this is the task of yours to complete this table. Otherwise, I will put this problem an assignment and I will give you the solution also. Okay? Just take it as an assignment for this. Now, I am moving to the next method, that is the searching methodology with the fixed step size. What is the assumption for this method. Again the assumption is that function must be unimodal, and we must be having the initial interval of uncertainty, and the initial guess point must be given to us, then only we can proceed, otherwise we cannot. How we are proceeding this, just to look at the process. We are starting from the point xi. Initially we are setting I is equal to 0. Now whether I will move to x1 in the left or x1 in the right, that is why we have to select that. That is why we are moving to the step 2. In the step 2 it is being said that find out the suitable direction SI. SI is positive if I move to the right, SI is negative if I move to the left. Okay? Now one thing is there, the fixed step size I will move, I will jump with the fixed step size. If I move to the right with the step size lambda I will move with the plus xi plus lambda I si, or I will move to the left. In that way we will get a sequence of x0, x1, x2, x3, x4, and we will get the solution. Okay? How to get it? I have just given one, I have just find out one problem for you. This is the function for us. Function is unimodal from 0 to 1, and it is given the initial starting point is 0, and we are considering the step size at point 2. That is why we are moving from x 0.2, then we are moving to initial interval of uncertainty 0 to 1. That is why, since I am starting from 0, I have to move to the right. Okay? I am going from point 2 to point 4 to point 6, point 8, in that way I am proceeding further and further. Just to see the difference between the functional values, you just look at, once I am moving through xi, the functional values are decreasing. We are trying to minimize the function. Okay? It decreasing and decreasing further and further, but there is a up where at point 2.6. Okay? Function is again going to up. That is why there is a check whether fi plus 1 is greater than fi or not. Once it is that, we are sure that around that point there must be the optimal solution. That is why we will go from 2.4 to 2.6, then again up to that the function is increasing, but beyond that there is a, I am sorry, function is decreasing, beyond that there is an increase of the function, but I do not know where the increase is. That is why we can declare the final interval of uncertainty as 2.6 to 2.8. And if you ask me what is the optimal solution, I will say take the mid value of that 2.7. But if you want to get the further approximation, that means further better approximation for the optimal solution, what you can do? You can take up a new problem as, take the function this one, take the initial interval of uncertainty at 2.6 to 2.8, then you take a very small step size, take 0.0001 as the step size, and you just run the iterative process again and again, then you will see that interval of uncertainty will reduce further and further, and you will get a better approximation there. Okay? In that way we can proceed and we will get the better optimal solution. And you could guess, even the function is discontinuous, if I do not get the functional value at certain point, I will just select the next, we will search for the next point where the functional value can lie. In that way I can proceed further and further. That is the nice part of this methodology, beauty of this methodology. Okay? This is with the step size, fixed step size. Again it may happen that we are proceeding point 2 to point 4, this is another variation. This is called the random step size. We can proceed even for searching, we can do the searching. We are not fixing the step size as 0.2. We could see that 0.2 to 0.4 it is decreasing, 0.4 to 0.6 decreasing, we can take a risk. Instead of taking the step size as 0.2, I will just jump, I will take the step size as 0.3. Then again we will see the function is decreasing. I can take another risk by taking the step size as 0.4, but by chance I could see somewhere the functional value is increasing, then I have to stop there. I will go back to the previous step and I will just take the smaller step size further to get the better solution. That is why what I suggest to you, though you are learning the methodology with the fixed step size, but if you apply in the practical problem, do not consider as a fixed step size. Even if you consider the fixed step size, write the program for it, take a very small fixed step size and run the iteration many times, 10,000 times, let the computer do it. Okay. Otherwise, you would consider the random step size, increasing step size, you will get the result better. Okay. Otherwise, as a beginner, if you proceed with the fixed step size, at least you can guess the optimum may lie from 2.6 to 2.8. Fine. I am moving to the next methodology. That is called the exhaustive search method. What it does, the whole interval of uncertainty, it breaks into several points exhaustively. Okay? That means, if there are the interval of uncertainty from 0 to 100, I will consider 10 points within that. I can consider 20 points within that, and I will see the function pattern at those points. Since the function is unimodal, from there we can guess where the optimal may lie. Okay, formally let me introduce the process. Now, here the initial interval of uncertainty L naught is given from A to B, where the optimum may lie. Then we will take n equally spaced points, okay, x naught to x n in between. Then what would be the each step length? Rather, the interval size, it would be 1 by n plus 1. Okay. Now, if I proceed like this, now we are searching for minimum value, that is why we will find out the functional value at x naught, x1, x2, x4 up to xn. Then at B, we are getting total how many points? N plus 1 plus 1, that means 2, n plus 2 points will get the functional value. We will find out the minimum, where the minimum can be there. Once we are finding out the minimum xk, we will consider xk minus 1 to xk plus 1 the optimum may lie. That is why what interval of uncertainty you are getting? You are getting the interval of uncertainty as L naught, size of L naught divided by n plus 1 into 2, because both sides I am considering together. Okay. Now, if you are happy with that, consider that, otherwise you consider that one as the initial interval of uncertainty. Again you take n equally spaced point, okay, and consider, repeat the process. And even the beauty of this methodology is that if I want that the approximation must be within 5% of the accurate value, I do not know what is the accurate value, but if I want to have the 5% accuracy, it is very much dependent on n, because 5% accuracy gives you this inequality, 1 by n plus 1 must be lesser than 5%. From there we could guess that value of n must be more than 20. That is why for getting the 5% accuracy, we should have 20 subintervals. Okay. Let us consider one example for this. There is one function, the function is very simple. This is continuous function within the interval x into x minus 1, and it is a continuous function within the interval 0 to 1, and this is my initial interval of uncertainty. Alright. We want to find out that where the optimum is there. That means we want to get a interval of uncertainty that is much more smaller than this initial interval of uncertainty. Okay. For that thing, what is suggest you find out through classical optimization technique even other than this searching process. I am breaking this interval from 0 to 1 with equally spaced, and each space I am considering as 0.1. That is why I will get 0.1, 0.2, 0.3, 0.4, 0.5, 0.8, 0.9. Here it is 1, here it is 0. Okay. Let us calculate the value of the function at each point. We will get the if we calculate, we will get the functional value as 0.09, 0.16, 0.21, 0.24, 0.25, 24, 21. You could guess where the minimum is lying. Okay. Where is the minimum? Here is the minimum. Minimum must be lying here somewhere. Okay. That's why if this is my xk, as I was mentioning that, consider xk minus and xk plus 1 as your new interval of uncertainty. That means that you consider 0.4 to 0.6 as the new interval of uncertainty. Okay. Now, what is the length of the new interval of uncertainty here? We are getting the length of the new interval of uncertainty as 0.2, all right. This is the solution for it. This is another method for getting the solution. I will just introduce the next methodology to you, and I will elaborate the methodology further in the next class. That is another searching process, that is called the dichotomous searching process, and with that I will just complete my class. Now, this is the dichotomous searching process. Now, as I was mentioning that initial interval of uncertainty must be given to us. What else should be given? Where the function is unimodal. In the interval of uncertainty, function must be unimodal. How the dichotomous process runs? It runs in this way. We consider the middle point and a delta neighborhood of that. And if we consider a delta neighborhood of that, then we are getting the two experimental points. One is the x1, another one is the x2. We will check that which one is the better candidate for minimization, x1 or x2, unimodal. Okay? That is why we will eliminate the region. What is the x1 value for you? The middle value is L0 by 2. That is why x1 must be minus delta 2, L0 by 2 minus delta 2, because delta is the neighborhood I have considered around the middle point. Okay. That is why you see with this process, what is the advantage if we apply this methodology? With this we are reducing the interval better than the previous one, because of this delta factor. Delta factor will reduce at every time delta by 2 or delta regions every time. Okay. That is the advantage. That means we will reach to the optimal solution quickly than the previous methodology. As I was mentioning, exhaustive search, unconstrained search with fixed step length, with random step length, any one of that. Okay. Now, we will take x1 and we will take x2. That is why x1 would be is equal to a plus L0 by 2 minus delta 2, and x2 would be b minus L0 by 2 minus delta 2 within bracket. Okay. And here now my x1 and x2 is there. Just I was mentioning the region elimination technique, x prime and x double prime. Now, we will find out the value for x1 at x1, what is the functional value, x2 and what is the functional value. Depending on that technique, there are three options only. Either one is lesser than the other, or the other one, or both should be same. Accordingly, we will eliminate the region further and further, okay, and we will just reach to the optimal solution at the end. What I suggest to you, with this idea, whatever knowledge you gathered with that, you start writing the algorithm for it, the steps, okay, and try to apply that dichotomous search on this problem f(x) equal to x into x minus 1. Okay. Otherwise, in the next class I will elaborate further, and in the next class I will do the dichotomous search and the Fibonacci method for you. Thank you very much for today.